Okay, so I will give this this lecture that I didn't have time to talk about during the 4 lectures at CTNT. So this will be the last one, I guess, supposedly to be the last lecture. So I will talk about so-called p-Adic version of Riemann zeta function. And this is called the Kubota-Leopold p-Adic function. So the basic idea is that, let me just call it LPS, but I will change for other notations later on. The upshot is that what the thing is it p-adically interpolate special values of the zeta function. In particular, the zeta function at the negative integers, which we know they are rational numbers if n is odd, and if n is even, then it's 0. So here's the meaning of this in a more concrete way, or like in a more, or I guess one way I think of this is it gives a systematic way to explain the following theorem of Kummer. Kummer, so-called Kummer's congruence, maybe. This is, let's say p is greater than or equal to 3, be a prime. And for any integer k, if n1 is congruent to n2, modulo, well, it's such a modulo a high power p, but also you want n1 and n2 to be congruent mod p minus 1. And also you want a technical condition that p minus 1 does not divide ni plus 1. For any, I mean, like, for any n1 plus 1 or n2 plus 1. I mean, like, they're congruent mod p minus 1, so one of the conditions is the same. It suffices. And also, I want n1, n2 to be greater than or equal to k. Then, with these 2 conditions, the zeta value at these negative integers n1, n2 are congruent modulo p to the k. Excuse me, earlier here, this should be p to the k minus 1. So I want to say that this Kummer's congruence was proved like in the 19th century, but people only get to understand what's behind it in around 1960s, when people started to develop p-Adic theory and the p-Adic function, and also develop this called USR theory. Let me sort of give an example of this. So p equals 7 and k equals 2. And in this case, we know we take 2 numbers, n1, n2 is 3 and 45, modulo 42, and you can check if this negative 3 is 1 over 12, excuse me, 1 over 120, and this is expands at 1 plus 7 times 4 times 7 plus dot dot dot, and the other one is negative 45, and this is a long number, is denominator 4, and this is like about, I think about 20 digits here. I'm not going to write. But then if you expand it p-adically, this looks like 1 plus 4 times 7 plus something. So at least the first leading 2 terms are the same. So they're congruent mod 7 squared. And I can also give an example. If this condition that p minus 1 does not divide mi plus 1 fails, these 2 will not be congruent to that number. So I'll maybe skip that. We can give examples of that. So now, let's talk about the proof of this. The first step is basically given algebraic way to access the special value zeta negative n. So this is related to so-called Bernoulli numbers. But our presentation is off by slightly. So let's quickly recall. We're going to do a little bit of analysis now. So I'm going to recall the gamma function, which is integration from 0 to infinity of e to the negative t of t to the s, dt over t. The reason I wrote dt over t is because this is, I think of it as kind of a multiplicative measure. Then, if I multiply the Riemann zeta function with this gamma s, then I get, putting these together, I get e to the negative t t to the s, and the sum of 1 over n to the s times this dt to the t. And then I can, if real part of s is sufficiently large, this converges absolutely, so I can swap the two integrations and swap integration with the sum. Now, if I put them together, I have t over n to the s. So now clearly, I can change variable. T goes to nt. And this way, I get negative nt and t to the s. The benefit of having this measure to be dt over t is that when I change t to nt, this doesn't change. I guess somehow a little bit easier that way. Now I can sort of swap back in these two, and we see that it's a geometric series. So I get integration of 0 to infinity of e to the negative t of 1 minus e to the negative t. That's the geometric series here. That's the sort of geometric series I have here. And I have time t to the s, t dt. And maybe I want positive powers of t. So I multiply the numerator and denominator by e to the t. So I get 1 minus e to the t minus 1, t to the s, dt over t. Okay? So let's rewrite what we have here. So now in this case, I can rewrite zeta s as 1 over gamma s times integration of from 0 to infinity of 1 over e to the t minus 1, t to the s, dt over t. So that's just sort of a way to change my zeta function a little bit. Here's a technical lemma. So I'm going to use this formula. Maybe I just put in a red box here. So this is a working formula for zeta. Sorry. Sorry, technical issues. Why can't I move? Oh. Okay, so I have some, okay, now good. It's very strange technical issues. So, okay, since we're going to prove a technical lemma, now there's going to be there was some technical issues. Okay, so here's a technical lemma. I'm gonna consider somehow this kind of expression here, and for me, I'll think of this middle one. This is some sort of particular function f of t. So my zeta s take this form of 1 over gamma s with this integration of this f of t with t to the s dt over t. And I want to say that for any sort of functions like this, there's a good way to express the negative value of zeta in terms of this function f as follows. So this is sort of a relatively general lemma, which I think is just tailored for our application. If you have some function on the positive part of the real line and it's smooth, it's called rapidly decreasing. Meaning that multiply with any high power of t to the n, the function will also always go to 0 as t is large enough. And also, I want TFT to be bounded on the other end as t goes to 0. So these are some sort of very technical conditions here. But of course, our f of t, this function, automatically satisfies this, because you see that if t goes to infinity, this e to the t is a huge number compared to any sort of powers of t. On the other hand, as t goes to 0, this e to the t minus t is roughly t. And therefore, I have t times 1 over t. So roughly is 1. So that's somehow leading term is 1, and there's some sort of fudge term. So it's anyways bounded as t goes to 0. Okay, so I have this. Then I can define the L function of fs. It's just some sort of fake thing. But I want to imitate what we defined for a zeta function. So that this expression kind of works in general. Like this. At least when real part of s is bigger than 0. Then this expression has an analytic continuation to all of s in C. And, or maybe I should say meromorphic continuation. Maybe it was, oh, excuse me, that's okay. Huh? This is a meromorphic continuation. And the thing I really care about is the negative value of this thing is equal to -1 to nth power of the nth derivative. So this is the nth derivative of f evaluated at 0. So this is the formula I really want. So I guess a corollary of this is that combining this with the above formula over there, that zeta minus n can be reached completely algebraically is minus n to the nth power times fn zeroth derivative with f of t being 1 over e to the t minus 1. Okay, so let's give a proof of this technical lemma. So let's prove. And of course, I have to minus some convergence issues. Since our topic is really PID numbers, so I'm going to be very loose on the analytic side. In fact, I'm going to assume that ft is 0 when t is large enough. But this is okay. In general, all such f will be kind of a limit of these things. You can modify the proof to make sure this is okay. So let's write down the definition and then do the calculation. So I have this thing, integration from 0 to infinity of ft t to the s dt over t. Okay. So I'm going to do a integration by parts. How do I do that? Well, I want to say, okay, I want to think of this as, oh, maybe just write directly. So I have this 1 over gamma s here, which is place here. And I have the function ft of t to the, maybe it's time to kind of note that now it's kind of combine these two together. It's a t to the sy minus 1. So if I do this, if I have this function, and I take derivative of that, that's precisely t to the s minus 1, which is what we have over here, right? If you do integration by parts, that means that you want to sort of evaluate this ft times t to the s over s at infinity and at 0, minus well, the thing. Right now you took the derivative on the first term. Now you want to take the derivative on the second term. So it's s times gamma s of integration from 0 to infinity of s prime f prime t, t to the s plus 1, excuse me, t to the s dt over t. Okay. Oh, sorry. I also write t here, so I have plus 1 here. Okay. So this is t to the s, and then breaks it to t to the s plus 1 over t. Just want to write things in a uniform way as before. Now let's look at the first term here. So this is where the conditions, the conversion conditions over here comes in play. Well, if t is large enough, this goes to 0. And somehow, or like I can even show it's, even assume it's 0. So therefore, at infinity, this is just 0. On the other hand, at 0, the same condition will also tells me that this is also, this will also go to 0, because my s, later on I'm gonna take my s to be negative numbers somehow. Excuse me. Sorry, I'm blanked. So I mean, sorry, excuse me. Sorry. I still want my real part of s is greater than or equal to 0. So therefore, this is this is 0. Okay. Now I have this expression over here. We're left with this. Now we note that this is a gamma function property. So this is the same as gamma s plus 1. So let's rewrite this, what we have here. If you look at it, this is the minus of L of f prime of s plus 1. Okay. And if you believe, as I said, so I'm going to ignore some convergence issues. And therefore, I'm going to assume that this does have a meromorphic continuation. You can kind of do it this way as well. And then, in fact, this will give, or I mean, should I say, somehow this give you a way to relate LFS with f prime evaluated as a plus 1. And you can sort of continue it this way and get to minus 1 to the n plus 1 times L of f nth derivative of s plus n plus 1. Okay, so now by some sort of continuation, you can show that somehow this holds even without this condition by continuation. And therefore, LF evaluated at the negative n will be the same as minus 1 to the n plus 1 of L of f n plus 1's derivative evaluated at 1. And then when that happens, this is just the same thing where the L function for, sorry, let's zoom out a little bit. So that's just basically, if you evaluate s equals 1 to this expression over here, gamma 1 is 1, and then you just get integration of from 0 to infinity of f of t dt, excuse me, n plus 1's derivative. And that's essentially sort of minus 1 to the nth power of f nth derivative of 0. Okay, so you can apply, so that's basically the proof, minus some convergence issue and analytic continuation, which I'm not going to talk about. So okay, so that sort of explains that our two-step process. First of all, I write my zeta function as some 1 over gamma, over 1 over gamma s of some integration like this. Next thing is that I realize that any integration like this, the L value of this thing at negative n is precise, just higher derivative of f. Now I can deduce a corollary that zeta minus n is just this derivative here. So let me copy this here to later because I'm going to use it. So here's a corollary. Now I want to talk about step 2. Now the benefit is that now I really have algebraic expression. I just need to sort of interpolate the derivative of an explicit function and evaluate at 0. So that's better, I guess. So p-Adic interpolation. maybe I should also point out that this is very close. This number is very close to relate to the Bernoulli number. Very closely related to that, but I will not talk about it now. So here's some technical note before I do this p-adic interpolation. So we know that this Riemann zeta function has a pole at s equals 1. So somehow the general philosophy is that, you know, whatever is true over the reals, it should work the same way over the p-adics. So we should expect its p-adic version, p-adic analog, has similar property. How do I mean, like, this is a little bit annoying. So for this, to avoid this sort of the pole here, pole is usually something a little annoying. So what we'll do is I will fix an A in Z and not divisible. In fact, what I want to do is I want to fix A in Z, then P does not divide A. And also if you do A mod P, this is a generator of Z mod PZ cross. Okay, I want to fix a sort of primitive, what's it called, primitive root. Like I want to fix like I guess I want to fix a generator of this multiplicative group Z mod PZ cross. This is just sort of some technical issues. And instead of interpolating zeta values, I interpolate this number instead. This is a completely purely technical issues. And you see that, you know, this number is well, I mean, it's 0 if n is -1, of course. If, you know, if, I mean, it's 0 if n is -1, and it's divisible by p if, I guess, if n is congruent to -1 modulo p minus 1. So somehow this is why in the Kummer congruence, we have to avoid this. Needs to avoid this. So this is somehow why we need to do this. Okay. So now let's do the interpolation. I'm going to consider a measure, as I said in the previous lecture. It's kind of a summary of this. I want to consider a measure called the mu of A. I mean, because it would depend on what this A is, the choice of A, on ZP, such that the Amish transform A mu A. I mean, the measure of A corresponds to a power series, right? So the corresponding power series, written like this, is equal to 1 over T minus A of 1 plus T to the A minus 1. So basically, you can kind of see that if you don't choose this A here, then you don't have this term here. Then somehow the p-adic function will be 1 over T. This doesn't quite belong to what you wanted to be a power series in T, because, you know, T 1 over T just is not a power series in T. So you have to subtract the pole here. So you see that when you have this A here, it kind of automatically get rid of this pole 1 over T here. But let's do it. Let's do it more carefully. So what is this? Let's do this calculation a little bit more carefully. Let's see. So what is this side? This is A. If you expand it out, this, oopsie. So this looks like AT plus A choose 2 T squared, and so on and so forth, right? I mean, it should be 1 plus, and then the 1 plus got killed. And now this is what? This is 1 over T. I mean, you A kills with this A here. So this will become 1 over T times 1 plus, I guess, A over 2 over A with T, and then A over 3, excuse me, A choose 3 over a t squared, and so on and so forth, right? And then you can do a kind of a Taylor expansion, right? This or geometric series. So this is going to be 1 minus this thing. And then plus the same thing squared, and then go on forever. Now what you notice is that this 1 over t here really exactly kills with 1 over t here. And then you're left with some sort of power series. And you can really check because the a is not divided by p, so this denominator a doesn't really matter. So all of these numbers are all sort of integer coefficients. So therefore it belongs to the power series, right? The EP double bracket t. It looks, of course, a lot neater if you write it in terms of this. But really, what it really is somehow this power series in t. And of course, the kind of a pole is related to that you have a t here. Then integration of or maybe I shouldn't try d mu, just mu a x. So if I put this measure and I integrate the function x to the n, I will get a to the 1 plus n power minus 1 times zeta negative n. Okay, so this is for I guess for n odd. For n even, this should give you 0 both sides, I think. So let's do proof. So let's see. So let's prove this. So you see that this is very interesting. That the zeta value can be interpreted as some sort of a measure in the sense that if you put some sort of power x to the n, some sort of a power, you integrate that power will precisely give you this zeta value. So let's prove this. It's just straightforward calculation. So let's see. So I integrate x to the n mu a x. What is this? I'm going to rewrite this x to the n as something different. Let's do. We can actually do it quite formally. So I want to write it as e to the tx. Excuse me, mu ax. So I start with the function e to the tx. I take a derivative that with respect to t, which is another sort of formal variable, has nothing to do with x, right? T is some sort of completely formal variable. So I take derivative with respect to t, so exactly n times. That's going to give me, because you see, let me just write it over here. So you see that d dt of e to the tx is precisely x to the nth e to the tx. Now after that, you evaluate t equals 0. So now this goes away, so you're left with x to the n. So these are the same. But I want to write it in a completely fancy way. Now this is equal to d dt and t equals 0 of integration of 1 plus e to the tx. Oh, I want to think of it as sort of e to t and then e to t to the x. So I have e to t plus 1 x mu a x. Now recall that the Archimedean transform, let me write it on the upper left corner here. For a measure mu, the corresponding power series attached to that is integration of the p of 1 plus t to the x d mu, or excuse me, I didn't have mu, it's just mu of x. Okay, so now this looks very much like that. Oopsie. This looks very much like that, except I'm going to take this to be my t. And that's exactly what you see here. So now, it's the same as d dt of n t equals 0 of a mu of e to the t minus 1. Right? By Archimedean transform, somehow this is equal my t. And this whole expression now equals to the Archimedean transform of that. But now we know that I chose my a mu t to be like this expression. So now I can really plug in. So what it is somehow, so I can plug in, really, let me maybe okay, fine. So this is what? This is 1 over t minus 1. So this 1 over t, the term here, minus a of 1 plus t. So that's e to the t to the 8th power minus 1. Okay. So I'm going to call this one fa of t. And what I'm doing is we know this is equal to that, and I'm taking nth derivative at t equals 0. So I can continue this. This is equal to fa nth derivative at 0. For fa t equals that. So now, now we have to compute this fa and derivative 0. So what this is let's continue maybe. This is 1 over, you have two terms. This is 1 over t to the t minus 1, taking nth derivative at t equals 0, minus a of e to the at minus 1, taking nth derivative, evaluated at t equals 0. Okay. So the first term, we call that my earlier theorem here, right? My zeta minus n, negative n, is minus 1 to the nth power times this nth derivative of this function here. And that's precisely what we're doing here. So the first term is minus 1 to the nth power zeta minus n, but n is odd, so. So you just get that. And second term is almost the same as the first term, except that we have on the t, I have some extra factor a here. And if you do a little bit of calculation, this is actually, you can see that this is just negative of a to the n minus 1 power of zeta. This is some sort of change of variable with the previous term. And then there's a negative term here. So therefore, altogether, excuse me, that's equal to a to the n minus plus 1 minus 1 times zeta minus 1. So that's our theorem. So that's our theorem. That if I integrate x to the n under this measure, I really get the zeta value. Okay, now I want to explain how to prove Kummer's congruence. So proof of Kummer's congruence using this. So let's maybe go back and then copy and paste the Kummer congruence to here. Let's see. So let's do this. So how do I do Kummer's congruence? Well, by theorem, we know that but by theorem, we know that somehow if I integrate, it's the same measure. I want to choose a as before. If I integrate x to the n1 mu a x, that's equal to a to the n1 plus 1 minus 1 zeta 1 over n1. And if I do integrate x to the n2 mu a x, I get a to the n2 plus 1 minus 1 zeta minus n2. Okay, so now I look at the left hand side. We note that x to the n1 is always congruent to x to the n2. Well, because I guess because my n1 and n2 are because n1 and n2 are congruent modulo p minus 1 to the p to the k minus 1, then these two will automatically congruent modulo p to the k. and therefore, because mu n belongs to ZPT with integral coefficient, this would automatically imply that, or maybe, sorry, the PID evaluation of ZP of x to the n1 minus x n2, will pair that with mu a, will be at least, or at least somehow this thing will be divisible by p to the k. So therefore, the thing on the left is congruent mod p to the k. On the other hand, of course, you can show that it's not that difficult to show that this the ratio of these two is also congruent to 1 mod p to the k. So therefore, basically, introducing this a doesn't really interfere with the congruence you want to prove. So now having these two all together, you deduce that zeta negative n1 is congruent to zeta negative n2 mod p to the k. And also, I should say this is not divisible by p. This is also used here. So good. So somehow this gives an interesting way to prove the Kummer's congruence. I think original Kummer's proof was to play with the I guess Bernoulli numbers, but now we interpreted everything in terms of our PID integrations. And what's, I guess, better is that somehow I have this interesting measure that really explains all these special values of zeta function. In fact, to get the so-called PID function, there's a third step, which is well, not quite. It's not that easy. It's not very obvious why we want to do that. But let me try to explain why we want to do that. So it's called restriction to ZP cross. So I have my mu. I have my mu a, the measure here, which is a measure on ZP. The correct PID function is actually, or PID zeta function is restriction of this PID measure to ZP cross. So let me give a definition first, and I'll explain, or I give some sort of reason why we want to do this. So the p-Adic zeta function. This is Lozano-Robledo. L function is the measure mu a restricted to ZP cross, or rather somehow maybe a continuous function on ZP cross with values in CP, QP. I want to denote this by mu Lozano-Robledo, comma a. Depend on the a, but then if you want to measure, I mean, if you want something without a pole, I guess you have to do this. So let me explain why restriction to ZP cross. So maybe we already kind of see a little bit of here. Over here, I need some sort of congruence like this. This is one reason. I mean, you see, I need some congruence here. So over ZP cross, this is okay. But then if P divide X, I really need, this is where I really need N1 and N2 to be both greater than or equal to K. But if you think about this, is a little bit strange. I mean, right? I mean, if P does not divide X, what I need, what I'm using is as some sort of multiplicative sort of order of this mod P to the K. But when P divide K, I'm really using sort of Archimedean norms of Archimedean absolute value of N1 and N2, the actual usual absolute value. And so you just want them to be large enough so that these are just both 0. The two proofs are of very different nature. So I guess somehow it makes more sense to say maybe this is not the correct thing to talk about at all. Let's just maybe ignore them. That's one way to see it from the proof, I guess. Here's a more philosophical reason. It's because, as explained in Keith's class, if I take the Galois group of QP and take sort of maximum abelian extension, or maybe I should say pro P, abelian extension of this. I know maybe I wanted to the ramified part. Unramified part is not very important, not interesting, I guess, for some reasons. Oh, excuse me, Q. My bad. Sorry. If you take the pro p abelian part of the Galois group of Q, this is the same as Galois group of Q adjoining all p power roots of unity. And Keith explained this is ZP cross. So this ZP cross is precisely the ZP cross I wanted to talk about. So this is a p-Adic function. It's canonically a measure on this, as opposed to sort of abstract ZP cross. I guess one should sort of conceptually understand that p-Adic function is a measure on this Galois group as a sort of canonical object. And also, this is also illustrated by, when we say integrate, earlier on we read, okay, integrate of this thing, of mu of something, right? Let me just write Copula A. There's a question of why x to the n, right? I mean, what's different? Well, like, why is somehow, okay, it's a monomial. But why is monomial so special from other things? But if I change this to ZP cross, this monomial is a character. The correct way to think of the monomial is a character of ZP cross with values in, say, QP cross, and goes x to, this is really a character. So that's the correct way to think of this. Somehow, you should think of it as somehow when you do this integration like this, you're taking a character of the cyclotomic, the Galois group of cyclotomic extension. So this is called a power of a cyclotomic character, I guess. And then evaluating that, and that character should give you L value. So I guess as data value. So that's somehow sort of the idea. So let me sort of state this actual theorem without the proof. It will take a little bit of time to prove this. So I'll probably just sort of skip this. For every n greater than or equal to 2, if I integrate x to the n of mu Copula of A, but on ZP cross now, this is equal to minus n and 1 minus, the usual 2 factors as before, and now I have 1 minus p to the n of zeta minus n here. So I have some extra factor here. Another way to think of this, where this extra factor comes from, is that I can sort of combine these two together. And I think of this as analytic continuation of zeta function, but I want to remove the factor at p. Remember, the zeta function has an Euler product structure, one taking product of 1 over L to the negative s, right? But if you think about it, so if you really take L equals to p, what you have here is 1 minus p to the negative s. But when you evaluate at s equals to negative n, this term, if L equals p and s equals negative n, this is precisely 1 over p to the n, right? Once you multiply that with 1 over p to the n here, that has the effect of removing the corresponding factor. So multiplying by this means that you remove the corresponding factor at p. So a factor at p removed. This is sort of the general philosophy going on. So here's a general philosophy. So suppose there's some so-called L function. For example, Riemann zeta function or Dirichlet L function, dedicated zeta function, or more general L function attached to modular form or automorphic forms, even more general. Suppose there's some L function, L something s. There should be a, maybe not quite a, or maybe some, or a or some. This is more technical later on. This is, let's just sort of, it's good enough to sort of think about this as a p-Adic function. As a, usually a measure on ZP cross So maybe call it mu of L. It will satisfy some properties like the following. So if you integrate on ZP cross of some sort of characters x to the n, mu L, this will be equal to some simple factors here times your L function, but not quite the L function. You have to some modification of the factor at P. And also the value here, n, corresponds to the exponent n here. So this is sort of the general philosophy. And even better, you can also insert here something called a character of z mod p to the nz cross with value say in qp say in qp bar, algebraic closure of qp. Okay, you can insert something in here, and that would have the effect of, just one second, let me change it to a different color. So that would have the effect of over here, you kind of a twist by some sort of psi. These should also be kind of equal. So that's sort of the general philosophy that whenever you have some sort of reasonable L function, there should be an associated p-Adic function satisfying this type of properties, type of properties. And of course, the question of whether you can construct such sort of p-Adic function, that's kind of actually a large industry that people are working on this, of trying to construct various p-Adic functions in the various situations. And this general sort of theories is in the framework of Iwasawa theory. A lot of people working on this. I'll end all my talks here, and I hope that somehow discussing sort of functions on ZP and talk about these measures, I'll talk about modular expansion and these measures and relating them to zeta values. I hope to interest you to study sort of p-Adic aspect of sort of number theoretical objects, in particular these p-Adic functions or p-Adic theory of this sort of characters or modular forms and so on and so forth. Okay, thank you very much for your time to listen to me. I'll stop here then.